Okay, here we are with an example, and throughout history, again, prior to graphing utilities, we use calculus to come up with graphs of a function. And so, if we were interested in graphing this particular function and having a decent amount of detail, such as inflection points, relative maxes and mins, with any type of precision we can do that using calculus here. And so here I'm going to go ahead and do that. Now, in this problem here, all we had to do was just select the proper graph, which I have this box. I'm sure some of you would like to have this feature in your software. It's in mine to show that it is completed. So option A is the graph of that function. And, it doesn't take a lot to figure out to graph it on some graphing utility and fill in the solution. But, at some point it's a calculus class. We want to know how to use calculus to do that. And so um, here we go. We are going to take and this function here and use the derivatives to analyze it. Why? Because the first derivative is going to tell us where functions are increasing and decreasing. Thus, that would tell us ultimately where the relative maxes and mins are, as well as taking the second derivative, and that tells us something about concavity, which in turn would tell us where the inflection points are. So, I'm going to go through just like I did in the other ones and find out where my function is increasing and decreasing. So I set the first derivative equal to 0. I find the critical numbers here. I factor out a common factor of 4x. Now, the x squared minus 12 does not factor into something nice and convenient. So if I, set this equal to 0, take 12 to the other side, I would just take the square root. So that solution would be plus or minus the square root of 12, which this is a little crunched in here, but that's approximately plus or minus 3.5. And that's going to be important when I, show you on this graph over here. Level of precision for those, where the critical numbers are, because, if I tell you something's, oh, that's square root of 2 or square root of 12, most people would have a difficult time getting an, intuitive feel for where that number is, but it is about 3.5. And so when I chart my function here, I chart the factor of 4x. And again, I put my critical numbers here. I'm just using the approximations of negative 3.5 and 3.5 for the interval, or for the two number lines. I'm doing one for 4x. So you can see I got positive values to the right of 0 and negative to the left. Now here, this is a little bit tricky, right? Because now, if I picked each of these intervals here, if I would put a number on, to the right of this number here, I would obviously put in the square root of 12 or 3.5, and you can do that in a calculator. You would find I would have positive values here, negative on this interval, and then positive on this interval. So when I take the product, that tells me my first derivative is positive on this interval, negative, positive, negative, which tells me where the function is decreasing, increasing, decreasing, and increasing. So I know that that's the fact, that's the situation. Now, I'm going to go on and do the second derivative here in the same way. I'm just going to set it equal to 0 and solve. And this one does factor down to, and for some reason my scan, I don't think, maybe it does show. Yeah, it does. The negative 2 and 2 here, excuse me, for my critical values, or my potential points of inflection, excuse me. And so, if I factor in, chart each of these, the 12's positive everywhere. And, I'm not going to explain all that. I've done that enough. But here I find my second derivative is positive on the interval to the right of 2 and also to the left of negative 2. And then it's concave down in between there. So, if I start taking all this information and going through that, you could use the process of elimination. I know it's decreasing, so, to the left of that. So again, that throws out, B and D right away. So I'm down to A and C. And, if I look at this one first here and I kind of get it, a little bit bigger, you could see that right here, I know that function should be, increasing on the whoop, I said this was the wrong one. Excuse me. That leaves me. I'm throwing out these two. Excuse me. So if I would blow up this one here, notice this kind of tells me right here. I know that's increasing up to 0. And notice, look what happens here. It starts decreasing here. So, there's 0. There's where x equals 0. I know it's got to be A. Okay. And if I would go through everything here, you could see that, I have a max or a relative min at negative 3.5, and it looks like these are every 2, 4, 6, 8, 10. Yes, every 2 units. So here's 2, here's negative 4. So that's about at negative 3.5, and then it starts increasing again. And all the way up to 0, it starts decreasing again. Then I go up to about 3.5 here again, because this vertical line here is 4, so that's 3.5, and it starts increasing again. And I look about negative 2. It looks like the concavity is changing from concave up to concave down, just like we said here. And then also at 2, same thing here, right about here. It's changing from concave down to concave up. Okay. So, this wasn't a multiple choice problem and it was an old fashioned calc quiz and they just said, sketch this graph. I could go ahead and use this information to do that. The only additional thing I would have to do is substitute these critical numbers and inflection points back into the original function, evaluate the function at those points of negative 2 and 2, or 2 and negative 3.5, 3.5 over the square root of 12, I should say, and 0. That would have been fun doing that without a calculator, right? You can see that problem would have taken quite a bit of time. Okay. But anyway, that's like I said, these multiple choice questions, and I don't know, some of you probably realize, hey, I'll just graph this in Desmos and match the graphs. And yeah, I guess you could do that. But again, this is how you use the calculus to go ahead and do it. So, okay, well, that wraps up that question here. We got another one after that, and that ought to do it for this particular week here, week 4 or homework 4. So, all right, we'll see you next time.